On grossit, ça roule, on grossit et on cherche à améliorer.
Let's start with about myself. I am a technical support professional at IBM for Ceph and storage. And I love to spend time doing integration of multiple technologies with each other and trying to solve some of the use cases and get them in somewhere. And I am also a certified architect level 2012, not 2. And by passion, I am an artist. I do calligraphy and do paper art. So if anybody is interested to give me the write your name in calligraphy, you can reach out to me. And let's start with the agenda. First, I will cover the basics, like what is the storage concept in a data pipeline looks like, and what type of storage we have. And I will cover where the gap comes in. And then I will cover very basic about NVMe-oF and Ceph architecture, that to understand the basic terminology about it. Then I will show the request flow architecture that for the code that I have written to integrate the OpenStack with the NVMe-oF, then with the demo, and finally I will show the use cases where we can use this type of basic for let's start with the storage pipeline. So we have the AI workload getting involved continuously in day-to-day life, like from how much it is using in our life, like from ChatGPT to different types of AI application. So it's not just limited, but with AI workload increasing, we also have our compute also getting increased, like NVIDIA having a very high compute power. But we have the high compute, but what about storage? If our storage is not going to be optimized and up to date with our compute, we are going to lag behind, right? The CPU, our GPU will gonna sit idle and not process anything. So that's one basic evolution of the storage growth for the AI. Like in the very initial phase, we have traditional ML algorithms like data, random forest algorithms, or something like KNN or nearest neighbor search or something like that. Where the data size is very megabytes, GB size of storage. But today we are at the LLM phase and it's going to consume petabytes of data, and in the future it's predicted that it's going to be physical AI where the AI agent needs to process its surroundings. So it's going to be consuming a lot of amount of data. So it's going to be exabytes. So one struggle we have is with the storage, the amount of capacity we can have, like how much storage we can save in the data. So that's one issue. Second perspective is, let's see, I've taken a very basic pipeline. It can vary depending on the type of AI workload you are running or application you are running, but it's very basic DevOps pipeline that you can understand it in an MLOps pipeline. So at first page we have data ingestion, that we have unstructured data, which could be files, images, or something, anything music or anything like of data, unstructured. For that we can most recommended is to have an object storage or data lake you can have. For next step is the data processing, where we will filter out which information is relevant. For that, it is recommended to have a file storage, because we are doing the processing and parallel file system is available, it would be great, but file system storage is a good one. Third is model training. In that there are two phases. One is training, another is checkpointing. So for both of them, it's recommended to have file system, but if we are doing checkpointing, we might use object storage also. And fourth is the model deployments, that serving and inferencing of the model. For that we currently we use VectorDB for RAG pipelines and model registry and caching. So for that also we recommend to have file system storage, or that's a usual recommendation, but we can have a normal block storage also. And last is the monitoring, where we will be storing logs and metrics. So that can be done on object storage or anything block file. So that's the basic pipeline. But in all of this pipeline, the key point for the storage would be that first thing that we want to notice, that the data volume consumption. That with the physical AI world, it's going to be increased very heavy. So we need a solution which can scale our storage consumption fastly. Second is the I/O performance bottleneck. Like in a RAG pipeline, we need to do a semantic search. If the storage is not going to return the results to very quickly, our RAG AI pipeline of the processing of the user data is going to slow down. Even though we have a high compute, but its RAG is not going to perform well, we have the slowness. Second, the cost and scalability. With that much amount of volume of data we are storing and this much of high performance, that's a trade-off, that if we are having a very cost efficient and scalable solution available. And the last is the access, that which data is going to be accessible and how much is going to be accessible. That's the same thing that I mentioned earlier, that AI training requires rapid I/O for the large data sets and frequent model checkpointing. And vector database requires low latency for their semantic search. And some of the, if you are using any analytical application in your AI related workload, like you have recommendation systems or something like that, any other application where the database is dependent for that. For that also you need a very high I/O kind of storage which can support that compute power. So if the slow storage is like, it's going to be expensive because it leads to GPU sitting idle, not doing anything. So that's the use case. I have presented out that where the problem is, that the storage where it's going to be needed right now for the AI application. Then let's make an intro and basic terminology about the Ceph and NVMe-oF. So Ceph is a software-defined storage solution which is going to be massively scalable. You can increase the consumption of capacity from terabytes to petabytes very quickly. And it's also self-healing. It's going to maintain the data integrity by itself, and if there is any replication feature is also there. And it supports multiple protocols. You can have block for RBD and NVMe-oF also, file for CFFS or NFS, and object storage. So you can, in a MLOps pipeline, you have three types of storage. You can use this Ceph to support all of that things in a scalable fashion. So that's the basic about Ceph. Then NVMe-oF fabric TCP. So this is a protocol which is used in a NVMe storage devices. Like it's using NVMe commands to send or store data in the NVMe devices. But instead of sending that in a local device, we are using that same protocol to store data over the internet. So NVMe or TCP concept is nothing that it's using sending the NVMe command to store data over the internet, and it's very simple deployment at it because it's using your traditional internet. It's not require any specific infrastructure. And you can think of it as a iSCSI for NVMe. Like in iSCSI we have how you store data, but it's for NVMe devices. So that's NVMe fabric protocol concept, and it provides you low latency because it directly store your data path. It's very direct. Not in iSCSI we have a kernel and then we store the data. It bypasses that. It provides very high throughput of the IO so that it would be really high efficient, and it's very widely adopted right now in the standards. So you can use it in any number of services. Like VMware is the most common one, you can use it, but it's an adaptive protocol. Now NVMe gateway in Ceph. So it is a service in Ceph which exposes the Ceph RBD image over the NVMe TCP device. So it provides you a block level access to Ceph, and it's integrated very easily. Like with a simple command you can deploy this NVMe over service gateway easily. And it can also provide a dynamic configuration. We can tune the scalability of the NVMe, that how much we want to have the performance. You can very dynamically increase and scale that. So this is the basic architecture, and NVMe gateway is in the center. Right side we have Ceph cluster, and left side we have a client, which the NVMe initiator. So let's talk about basic terminology in NVMe gateway. Okay. So first we have a namespace which is equivalent to LUNs in iSCSI we have, or it can be directly mapped to an RBD image, like single RBD image. You can represent any namespace as an RBD image. Second is NVMe subsystem. So subsystem is a group which contains the namespaces which and other elements like controller, and it also provides an end-to-end unique identification to which we are connecting to the cluster. RBD and image. It's the same thing that we have in iSCSI. The same thing in iSCSI we have IQ and that iSCSI qualified name. Here we have NVMe qualified name. So, and IO controller, that is part of subsystem. It's basically a connection. It maintains one unique connection to the client initiator, and where it's going to send you NVMe commands to perform the respective operation. Listener is basically the IP address or port number where the client is going to connect to show the data. And gateway group is a high available feature in NVMe-oF in Ceph, which groups multiple gateways. It's from the scalability perspective, that multi-path concept, that it's going to scale and group multiple NVMe gateways into a single subsystem to provide high availability multi-path concept to the initiator. So that's the basic terminology, and if you can club them together, this is how it will look like. That gateway will have NVMe-oF target, which act as a target also, and client for the Ceph also. So we have subsystem, and in each subsystem we have a namespace and controller. So that's the same thing architecture, that if we club them in together. And for the configuration, like because we can also configure the NVMe gateway very easily. So that's how you can using a RPC client or gRPS. You can configure the NVMe gateway configuration also. And this is the multi-path part. Like you can have one subsystem in which you must scale out multiple gateways so that you can provide a multi-path or high availability feature for the client. So this one is a performance that is achieved by the NVMe gateway with using a PO tool, FIO tool, and it's using a 32 client connector. And the important part that here we have to note is that at the bottom you can see that there are a number of block devices. That's a namespaces that we mentioned, the RBD image. With one block device image, it can scale up to very high number of IOPS. So with that concept in mind, I can that's how I designed the POC or the code I have written in that concept, that using a single block device you can scale it up to very easily to large level. And same thing you can have in the different graph, that different scale of nodes on the structure. This one is one block device and previous one has some other two block device, even different type of scaling. So that's the performance review. You can find it on the online also. This is predefined, already done. I have not done it, but this is the one to show you that the defined performance it can scale. Okay, now let's see how it connects to OpenStack volume to Ceph NVMe-oF. So in this diagram, I'm going to show how Ceph, OpenStack and Ceph service are going to interact with each other and based on the how I define the code. So it's not a production ready, it's very dummy that code I designed to use that OpenStack with the NVMe-oF service. Okay, so these are the 4 services. So first is the volume creation request, in which it will create a normal Cinder service you have for the RBD. It will create an RBD image and provides you the details. Second is this connection, the gRPC connection that I initially mentioned in the diagram, that is using gRPC to configure NVMe subsystem and all of that resources. So in this one, it will create, when we attach the volume to the server, it will create the NVMe subsystem, exposing that RBD image that we created to a namespace, and then provide a connection detail to the Nova service. It will send the same to the return that, and it will send that to the Nova service to map the NVMe on the device where the server is running. And the third part is the terminate connection, in which it will remove the namespace, TNF resources, and everything. It will do that. So that's the code I designed, only 3 things. When we attach the volume to the server, it will create the resources, and when it removes, it will destroy the resources. In this one, this is the initial design I made, but later on I made some changes that if I am doing the same thing again and again, I don't have to create subsystem again and again all the time. So that will gonna waste the resources. So I created it like it won't remove the name subsystem. It will remove the namespace only, because the RBD image is mapped to a namespace. It will remove namespace only. Let's see a demo now. So in this one, first I created a volume type for NVMe-oF, and in this I set the backend. So the backend I have and if you see so this is the backend. If you see the volume driver, which pool it is going to use. Let's say for creating an RBD image, I have mentioned it over here. And below we have the gateway address, which is going to connect to a NVMe gateway deployment that you have done. And there are 2 additional configurations that I have added, that if you want to destroy your subsystem when we delete the volume, that you can also keep it as an optional part. So I have also set that as a configuration. Before when creating a volume, this NVMe CLI package needs to be merged, because without this we are not going to be able to use the NVMe-based command on the client node. So these are the must ones which needs to be done before on the client side. Now it's unavailable. If I go back and see the so this is one server that I just used to keep it running over there. So we go back of testing this code, so I kept it running over there. And if you see there is only one device which is attached, and this is a normal procedure that we have in OpenStack Nova service, that it creates in the VMs pool. Create a device for the root device for the system server. Now if we attach this volume, that NVMe-oF volume, to this one, we will see connection is created for the NVMe device on this one. So it's the same, it is and the RVD image that we created is going to expose that same, and you can also see it will get attached inside the virtual machine. And here if you can see that it will create a subsystem for that same image. And I also created a name page. In the name page you can verify the image name is the same one which is available for the RVD one. So it is mapped to that name page also. It's a one-to-one mapping. And one-to-one mapping I did because as you see the performance graph, it's going to be very easy to scale the performance so that we can provide that much feature to our end user on the AI workload. And the same it will have the listener also. And if we delete this volume, it should remove it from the VM server that will be attached. You can just see in the above one, it got attached. But so far I did not, in that this one I did not created that removing of the subsystem part, because I thought that if I want to remount that same volume to a different virtual machine, because in AI workload we might need to mount that same data to a different application, like read-only application. Like one training pipeline is using one set of data, another pipeline is using different multiple sets of data. So for that purpose, when we detached the volume, I did not deleted the namespace or subsystem, anything like that, because if a new client want to reuse that same volume to a different server, they can directly just remap it. So it doesn't need to recreate all of that resources. That's why I did not destroy any of these resources. If you can see, they are still present over there. But when we delete the volume, it will gonna destroy the namespace, because the RVD image is lost, mapped to single RVD image, it will delete that. So once you do that, it will, this NVMe list is empty. And the same thing you can see, the system and everything will be there, but the namespace will not be there. The namespace is empty, but other two will be there. So that's for the demo. Let's show the use. So there are two use cases that on which primarily I have designed it. That for the vector database, if you are using a RAG pipeline, which is a very common LLM in the company, that RAG is a real requirement. Vector database is also need to be scaled. It can be scaled with a very low latency. Like if you are using multiple large amount of RAG data, because every RAG you need data, you need to create a vector data search for that, which is an embedding model. You create an embedding vector for that, and then you store that vector, and that can be on different bits. The most common one is a 786 bit matrix, but if it's going to scale with the more features and the large amount of storage, very low latency is required. So in that case, this NVMe-oF is a very perfect solution for that kind of scenario which we are running. And it also needs to be scalable. So if you are using a large amount of data, then it also needs to be scalable. Second is the database. So you can use the same thing in a database also for mount your database applications. So that's it from my side. If you have any questions?
Yeah, I have a question. So, like, you, in this use case, specifically, you're actually using anyway, like, the RVD backend instead. So, comparing the performance of actually mounting, like using NVMe-oF fabric, but on top of RVD, does it actually give you better performance than actually the QM direct mount of RVD via, I don't know what it is, like, RVD, I guess.
It would depend because since it is the NVMe-oF is on top of RBD, so RBD performance will be the baseline for that, right? How much it's gonna give to you. But depending on the workload, like if you are using a very small file, very small amount of data. So for that amount of data, it's not going to reach out to block Ceph cluster. It's gonna NVMe-oF gateway itself will provide that much performance, so it will be scalable.
So the NVMe gateway will actually perform some action in the data path. So not everything will be persisted automatically in the RBD.
Direct you can do, but it will not provide you that latency, low latency. It will not provide that. For the low latency part, that's a very key part for NVMe-oF protocol, that it provides a low latency. So that's why NVMe-oF gateway will be most in that one.
Yeah, but what I was wondering is like if you really have low latency with the gateway and you don't have it with RBD, it means that the gateway is kind of masking the operation that they are actually going down to the storage.
You can do it. It's not. It's a very trade-off thing, that which one is more suitable for your data workload pipeline. Because in the starting I mentioned that that's a very basic MLOF pipeline I picked up, but it can vary. Like in that one I mentioned the file system storage is the most suitable one for checkpointing. But if we are having a modern checkpointing, it will like sometimes it's done in terabytes or GB. So in that one, file system might also lag. For that one, you require very low latency. Till the checkpoint is done, your training is not going to resume again.
Yeah, no, but that's perfectly clear to me. Is that you just don't understand the comparison between RBD plus and the NVMe-oF fabric over RBD. Whether like this is like if it's really like better latency wise, I wonder how. But like
it's not like it's a very trade-off. It depends on the workload.
Okay. Question: how are you handling the HA, so high availability of the connector translator between NVMe-oF fabric and RBD?
So if you see the initial starting graph, this one, so you can see that both of the gateways are like one gateway is connecting providing one path and another gateway providing another path, but both are for the same subsystem.
Okay.
So it's providing like multi-pathing, that two different HBA, providing the data access path.
Okay, so we need like two RBD images per one virtual?
No, it's the same RBD image.
Okay.
It's the same namespace. There are not two different namespaces. In one subsystem, we have one namespace, but there are two different controllers comes into picture. So two different controllers, and they will make two different connections with the client.
Okay.
Is the gateway actually aware if I'm actually assigning NVMe's to him, or could I just use normal SSDs or even HDDs?
On the Ceph side?
Yeah. Would it notice it? Except that it's slower, of course. But
Yeah, you can separate it out with the NVMe-off devices based on the full configuration, which type of RBD image you want to use. So you can separate it out. You can use it in a normal standard also, HDD also. That's the Ceph part. Right? NVMe-off gateway is also client to Ceph, which is using RBD images. So Ceph can provide whatever it wants, but we have to configure which we want to use in the NVMe. So using HDD in NVMe is not a good design. It's going to be bottleneck for that.
But for SSDs, do you know if this protocol would have an advantage over normal block device for OpenStack?
Yeah, it will be using normal IC, normal wires also. It doesn't require any specific, like earlier in a fiber channel or something like that. It will be your normal IP or internet protocol.
You mentioned RDMA support, but Ceph implementation, I guess, is only TCP/IP implementation of NVMe-oF fabric. Can you clarify? You mentioned the use of high performance, like to bypass TCP stack by using RDMA plus TCP.
Yeah.
Does Ceph support RDMA on NVMe-oF fabric implementation on the gateways?
Let me get the question. Is this for this one? The one slide?
Yeah, it was not on the slide. It was like on the slide mentioned like high performance networks of like RDMA based Yeah, there is a RDMI network cards, but does Ceph implementation support on NVMe-oF hardware?
Yeah, Ceph supports NVMe-oF everything, but not in a native protocol. Like in a native Ceph, it doesn't support that. That's why it has a separate service. That's in the initial card. That it's a gateway. NVMe-oF is a protocol, and NVMe gateway provides that. So it's basically a target and a client for the Ceph. So it's a translator for Ceph RVD email interface and an NVMe-oF protocol.
Yeah, but for transfer, does it able to use RDMA?
Sorry?
Remote memory writes without TCP like direct to the client, from the client to the gateway.
The NVMe-oF, no. Without this gateway, this protocol will not gonna use it. If we remove this NVMe-oF gateway, this protocol will not come into picture. You can directly map the RVD that he asked that. You can directly use the RVD image also, not using this NVMe-oF.
It looks like the transfer protocol, like for transferring data, is TCP/IP.
Yeah.
Yeah, and you mentioned, I don't know, maybe from one of Phil's slides. Yeah, that's TCP and RDMA.
Yeah.
And RDMA is completely not a TCP.
Yeah, RDMA.
Just like directly writing. Does it support it?
This
Can
slide
we use
is
the
for-
modern NIC cards to just like
Yeah, so this
triple
slide,
performance?
yeah, this slide is for NVMe-oF protocol. So in NVMe-oF,
Okay.
we have TCP and RDMA protocols as well.
But not in Ceph.
No, not in Ceph.
Okay, now you answer.
My question was related to RDMA support.
Sorry?
So currently the gateway is not supporting the RDMA protocol, only the Ceph cluster, right?
Sorry, I have hating for
Sorry.
Can you repeat?
I will repeat. So currently, according to my understanding, the gateway is only supporting the TCP protocol and not the RDMA protocol.
Yeah.
Okay, and do you know if there is any plan to support it in the near future?
For Ceph,
Sorry?
for in the Ceph,
Sorry,
within the Ceph protocol.
yeah. No. In the NVMe, between the gateway and the client.
Yeah. So yeah, it has a like mapping of the command. It uses PDK library which maps the protocol and all the commands. But in a native Ceph, we will use
Ouais.